about soil carbon research. Dr. Budiman has a close collaboration with us, particularly in Professor Stott's group. I think most of us would know him. And Professor Budiman Milasli is a professor in soil landscape modeling, and he is also the same leader of soil, carbon, and water at the City Institute of Agriculture, and is recognized as a high-cited researcher in 2019 by the Web of Science. Professor Milasli the research and contribution to the discipline of soil science has been on discovering the causes and controls of soil distribution over space and time. He also created some novel methodologies that try to explain the dynamics of soil in the landscape. Today, he will give us a talk or a short course about soil carbon research. So his topic is understanding the drivers and distribution across scale. So welcome you, Budiman, and now we pass to you. Thank you.
Thank you, Professor Luo, and thank you, Rui, for organizing this. Good afternoon, everyone. It's a pleasure to share with you a general lecture about soil carbon and research. So this is a general lecture, so a bit about the understanding of soil carbon and also a bit of research that we are doing. So if you want, for example, if you have a question or whatever, you can put it on the chat. There's a chat screen, I think. If you type it in later, if I see it, then I can answer it as well. Okay. So, so as we all know, carbon is a soil carbon or soil organic matter. Soil carbon particularly is an indicator of soil fertility. So when we talk about soil carbon, we want to have a soil with high carbon content. We know that because soil with high carbon content usually is a highly fertile soil. But carbon itself is a currency of climate change. So what do I mean by currency of climate change? So if you look at this graph, probably you have known it all. It's a famous graph. So the blue one is the CO2 concentration in the atmosphere, in the air in Hawaii. So they have monitored this since 1960s. And when they monitor it, because why in Hawaii? Because Hawaii is a very, very nature place. It's not many industry at that time. It's a very clean air. So when they monitor it and look at it over time, they can see that over time that although that's periodic, that means that within a year there's up and down depending on the cycle, but over time there's a very high or is increasing CO2 concentration in the atmosphere, right? So in the around 1975 in Tasmania, they also want to know the concentration of the CO2 in the atmosphere. So they go to Tasmania. So if you know Tasmania, Tasmania is an island, not in the mainland of Australia, but an island south of Australia. And if you see the picture here, and there's this Cape Grim is a little place here. And why they choose Cape Grim? Because that's the location with the cleanest air. Cleanest air. That means there's no industry at all. So there's a place, the freshest air you can get in Australia, right? So they also install a monitoring site to monitor the CO2 concentration of the air. So ideally, if there's no pollution, the air in this Cape Grim should be very clean because this is the cleanest air. There's no industry, there shouldn't be any pollution. But over time, they also see that the same trend as well happened in Tasmania. So this is the very south of Australia. So there is a trend of increasing CO2 in the atmosphere. Right. So if you look at this, the concentration we have at the moment, this is around 2019 or 2020, is above 400 ppm in the atmosphere. So the concentration of CO2 in the atmosphere is around more than 400 ppm. So the last time the Earth or our Earth experienced concentration of more than 400 ppm is during the Pliocene period. That is around 3 million years ago. So we haven't experienced this high concentration of CO2 since 3 million years ago. And during that time, the organism that live on the Earth or the life on Earth is not like currently. There's no human. It's giant mammals. It's something like this, right? So this is 400 ppm concentration of CO2. That's so what we have seen is the highest CO2 concentration since a long time before us, right? So that's why people in all the nations agree, what we call as the Paris Agreement. So this is during a conference in Paris several years ago. They have an agreement to keep the increased global average temperature well below 2 degrees above pre-industrial level, or to also limit the increase to 1.5 degrees if it's possible. That means that we shouldn't our temperature should not increase more than 2 degrees, or 1.5 degrees is even better, right? So most of countries in the world have ratified or signed the agreement to keep the CO2 down, so that the temperature will not rise more than 2 degrees Celsius, except few countries. So when we talk about global warming or climate change, we talk about carbon, right? So why carbon? So this is because this is CO2 that is in the atmosphere is causing a lot of imbalance. So if we talk about carbon, we have to talk about stocks and fluxes. Stocks, that means how much is stored in different places, and fluxes, where does it come and go, right? When we talk about stocks, that is amount that is stored in the system, in our Earth system. So in the atmosphere, that's about 830 billion tons, or usually called gigatons of carbon, right? And the vegetation is around 500 to 550. And the topsoil is around 860. And if we look at all soil, so this is for the whole world. So up to 2 meters, that's around 2,400 billion tons of carbon, right? So this is what we call a stock. So what is stored in this system? But it's not always stay there, because there's fluxes that is going in and out, right? So there's a carbon that is being absorbed by the plant. So this is going to make the plant, but there's also carbon that's being emitted because of the industry, of the cars and everything. So this is around the fluxes every year that is going out in the atmosphere, or going to other places. And then there's also fluxes due to land use change. That means that previously it's a forest, it is a carbon sink. That means it's store carbon, but then if you chop down the tree or other things, there's lots of decomposition happening, and there's fluxes. So in total, the human induced CO2 change or carbon change is around 9.8 or plus or minus 0.9 billion tons of carbon every year. So it changes every year. It's increasing every year. So, but there are places where it absorbs carbon, like the vegetation, or some of it goes into the ocean, and some of it, but most of it, that means most of it is in the atmosphere. Right? So this is fluxes over time, CO2 fluxes over time. So this is in terms of CO2 fluxes over time. So this is positive, means that it is going out, and negative, that means that it's going in or being stored, right? So ideally, we want it all to be a sink. Sink means that all the CO2 is going to be stored, for example, in the ocean, in the land. So in the land could be in the vegetation and in the soil, or some of it is in the atmosphere. But a lot of it is because of the imbalance. That means most of it going out of as a fluxes, as a positive value, right? So all the positive value goes into the atmosphere, right? So if we want to, so if you go back here, so this is the historical period from 1900 to 2016. We have seen an increase in the fossil fuel, and increase in land use change that causes an increase of CO2 flux. So if we project it further, if we project it to the future, we can see that if we keep going, the CO2 concentration will keep going increasing, right? So it will increasing. This is what we call as business as usual. It will keep increasing. So if we put mitigated greenhouse gas emissions, that means, for example, if we change some of our practice into, for example, windmill, solar farm, and other things, this is conventional abatement technologies. So we will decrease the CO2. It will decrease, right? So if we don't use so much fossil fuel, if we change to solar panel, if we change to wind farm and other renewable energy, then the CO2 concentration will be decreasing. But it's not enough, right? Because the decrease will be only up to here, right? So if we want to have what they call below 2 degrees Celsius CO2, we need to have a much more decrease in greenhouse gas emission. And at some point, we should not be emitting CO2, but we should be removing CO2 out of the atmosphere. And this is what we call when the flux is negative. When the flux is negative, that means we have removed the CO2 from the atmosphere to put it somewhere else. And this is what we call as negative greenhouse gas emission. So that it's the greenhouse gas emission is not positive anymore, and it should be negative. And to achieve this negative greenhouse gas emission, we need to have carbon removal technologies, right? And what are the options of carbon removal? So this is called negative emission technologies, right? Negative emission technologies. So this is terrestrial negative emission, sorry, not terrestrial, but so there's also in the negative emission technology. So that it means that technologies will help remove emission. So it's not positive emission, but negative emission, right? So what are the options? So first of all is afforestation or reforestation. That means that you plant more trees. You can absorb CO2 from the trees. And the second option, if you use biochar or soil carbon sequestration, that means that you put the CO2 in the soil with some practices, which we will discuss later. The third option is ocean fertilization. That means that you put fertilizer in the ocean so to enhance, so that in the ocean it produces more biomass. If the ocean produces more biomass, that means that it can absorb the CO2. And the fourth one is called bioenergy with carbon capture and sequestration. That means that the factory is using renewable energy. For example, it use windmill, or it use solar energy, and all the materials are recycled. For example, it use the tree. Some of the biomass can be burned into the for fuel, but the emission is captured back in the tree and the soil and so on. So it's sort of a closed loop energy system. And the fourth one is enhanced weathering, because weathering of the soil or weathering of a rock can absorb CO2, right? So this is in terms of soil chemistry. And the last one is direct air capture. That means that you have to put like a big fan that suck out the CO2 from the air and put it somewhere else, and put it in the soil or in the ground or somewhere else. So these are negative emission technologies. So these are what available in the literature, in the market, and these are what people are talking about. So, but what are the feasibility of doing all of this, right? So this one is still a lot of work needs to be done. It cannot be done all the time. And weathering, it's theoretically it can be done, but for large scale, that means that you need a lot of energy to break the soil, to break the rock, to get. And direct air capture is still a very expensive technology. That means if you want to have a fan, that means that you still need to generate the energy for the fan. Ocean fertilizers, it's still not applicable for a large area. So the one that is probably feasible is forestation. Forestation, that means planting tree, but of course this cannot happen everywhere. In some places it might work. And the one that can be applied everywhere is soil carbon sequestration. That means that putting the CO2 in the soil while we are doing cropping, while we are planting crops, or while we are creating crops. Okay. So this is why soil become part of the soil can become part of the climate mitigation, climate change mitigation. That means that part of the solution to reducing CO2 emission. And during the Paris Agreement, there's also a program called by the French government. It's called 4 per 1,000. It's called 4 per 1,000 soil for food security and climate. So what it says is soil for growing food security by food security. While we're doing that, we can also use it to fight climate change. So why does it, what is 4 per 1,000 means? It's saying that because annually our CO2 emission from fossil fuel is around 8.9 gigatons of carbon, or 8.9 billion tons of carbon, which we talked about earlier. But organic carbon in the soil is quite a lot. That's if you took the soil of the world around, there's around 2,400 gigatons of carbon, or billion tons of carbon around the world. That means if we compare this 8.9, this annual emission, compared with the total global storage, it's just 4 per 1,000, or 0.4%, right? So theoretically, if you increase the soil carbon by 0.4% throughout the world, that means that you can effectively remove the CO2 that is being emitted by fossil fuel and put it in the soil, right? So this is 4 per mil, or 4 per 1,000 means that amount of carbon stock increase is about 4 per 1,000 to offset the CO2 emission from fossil fuel. But of course, this is not going to happen everywhere. But it's an initiative, and it's a good thing that is because soil can be used for food security and climate change. Okay, so that's why there's a lot of research on soil carbon, and then what we call a soil carbon sequestration. That means that we take the CO2, new practices that we take CO2 out of the atmosphere and then put it in the soil. So the other thing that maybe I need to clarify, when we call negative emission technologies, that means that in order for it to be negative emission, it has to be a new initiative, right? For example, when we say forestation, that means that we have to plant new trees in order to absorb CO2. So existing forest is already exists, so it's already in balance with our ecosystem. So there's no negative emission. So when we talk about negative emission, it has to be a new initiative. That means new practices that increase the CO2 capture. So when we talk about soil carbon sequestration, new practices that will help increase soil in the carbon in the soil. So if the soil is already existing, is already fertile, it's already have a high carbon, then it's not a soil carbon sequestration, right? So here I'm just going to talk briefly because the research can scale from a nano scale to the global scale. So this is only a short lecture. So this is only a lecture. So we cannot cover everything. So we'll go through several examples to see how soil carbon, understanding soil carbon or helping soil carbon maybe can help us to do research and which can help solve the problem, help the problem of the reducing CO2 in the atmosphere. So because soil is across all these dimensions, so the area that is affecting the soil carbon is also going to be different, right? So this paper, this link, which you can look at it later, they summarize it's a review paper. They talk about what are the drivers of the soil carbon storage at all these different levels. So obviously from a small scale, which we'll talk about later, it's driven by the soil physical chemistry, about the clay minerals and about the aggregate, about the clay minerals, about the calcium and magnesium and so on. So at the particle level and then at the aggregate level is also controlled by the soil physical chemistry. So at the farm level or the plot level, so it's now controlled by there's interactions between topography and organisms and the soil and then the land use. So when we talk about regional, so it starts to come more about the climate is going to affect how the soil is going, the climate, what is the potential of the soil going to have on carbon, and also vegetation and the type of soil and also the management. And at the global scale, climate will have a very strong signature, which we'll look at it later. So let's look at first at the profile level. So when we talk about soil structure, so when you learn about soil structure, you are looking at the shape of this soil structure that happen in the field. So the soil does not occur randomly; it has this kind of structure, and each of this structure means that it has a shape. The soil itself arrange itself in a shape. So what makes it do that? So it's an organization that is made up of different things. So for example, this is the A horizon. If you look at it carefully, it is made up of different aggregate size of aggregate. There's macro aggregate. Within this macro aggregate, there's also many micro aggregate. And if you look into the micro aggregate, there's also a lot of interaction with the organic particles and the mineral parts, right? So all of this is related, and this is how the soil makes the aggregate is to do with, because it has a wetting and drying cycles, it has root and organic matter, and it has the soil fauna and flora that helps make this aggregate. And all right. And carbon is very important in this, right, in the forming of aggregate. So this is one model of the aggregate. So this is a conceptual model. So this is how it's realized. So it says that the aggregate, this is one piece of aggregate that's called an aggregate. So it's made up of a macro aggregate, different macro aggregates together. And within the macro aggregate, there's also a so this is one big macro aggregate. It's made up of little micro aggregates, and within these micro aggregates, there are different components. The ingredients are the clay microstructure, or clay silt size micro aggregates. So these are the mineral part. And if you look at it, the brown one, this is the plant and fungal debris. So these are the organic matter where it has a lot of carbon. So the role of organic matter or carbon is that it binds all this aggregate together to form a micro aggregate. So when it's in the micro aggregates, the carbon is in the micro aggregates, it's also being protected, right? That means that other microbes will have difficulty in eating, trying to get access to this carbon or organic matter inside the micro aggregate. So different micro aggregates is also being linked by all these plant roots, big plant roots, or the green stuff, mycorrhiza, fungi, and all the pink, the red stuff, particulate organic matter. That means organic matter from the plant that has been eaten by bugs. So all of this is linked together to form a bigger aggregate. So you see that carbon or organic matter plays an important role, not just for climate change, but an important role to make the structure integrate the integrity of the structure. That means that it helps to put it helps the soil to stay together. So what happened if the soil if we have a soil, and how do we make this aggregate? So there are different studies. They want to see if we start from a soil without anything, with just mineral material. So here they just put a mineral material. So they just put clay, right? And then they start adding organic matter to it. So within a month, several months, you see that this soil that initially doesn't have any aggregate, right? Because of organic matter, over time it forms into, within 15 months, it forms into this little clots of aggregates, what we call macro aggregates. So this is what defines the soil. So if the soil is inert, there's no organic matter. If it's just pure clay, it will be like this without any aggregate. So this is just after 15 months, just several months, you have a aggregated soil, right? Because all the bacteria and fungi will involve in making these aggregates, and because of there's also organic matter, right? So this is an experiment that our colleagues do here. So they do similar things. So first of all, they take the soil, the pure mineral, right? So, and then this is the water stable aggregate. So after 42 days, so just 7 weeks. So if there's no carbon, if you don't put any organic matter in it, the water stable aggregate is 0. So there's no aggregate that's going to form. So if you put it a bit of organic matter in terms of glucose or sugar, you suddenly see that there's a increase in water stable aggregate. That means that the organic matter with the help of bacteria and fungi will start create this aggregate. And if you have cellulose, you also create this aggregate, right? So you can make this aggregate just by a simple experiment. So if you start with a pure clay, nothing in it, no organic matter in it, and then if you add a bit of organic matter, and then there's some microbes in it, within a month, you will see that it will start to form aggregates. So this is make the soil alive. And we can look inside what's happening in these aggregates. So with the CT scan, tomography scan nowadays, that you can look into the particles, microparticles. So you can look into the mineral part. So this is the mineral part, about what is the composition of the mineral part. So if you do the architecture, then you can see that this is the part of the mineral. So this is how the mineral looks like. But then if you can see that, you can also see what's the part that are not mineral. That means these are the pores. These are the pores that are created because of the aggregation, right? because they are aggregates that there are pores in between. It's not just pores, but it also has a network. It also has connected to one another. So this is what makes the soil alive, because it has the porosity, and then the porosity is connected to each other in a network. So this is where all the fungi, all the bacteria will live. And then different types of material will create different types of aggregates. So this is also the CT scan, and then it will create different types of porosity and so on. So now with this, we can do 3D post-scale modeling. Then we can see what's the effect of different types of organic matter and how it influences water, solid, and water movement. So this is the fundamental studies that people are looking at. So why? Because they want to understand how the organic matter, how carbon with carbon, it's not just adding the fertility, but how it's stored in the soil and how it forms aggregates. So these aggregates will in turn help to protect the organic matter or the carbon from being oxidized by other microbial. So the one thing about the importance of this aggregate or soil structure is that if you don't have a good soil structure, then you'll have a loss of fertility. And that means that if you have loss of fertility, you have a reduced biological activities. Then at the end, you have a change in soil water regime, that the soil doesn't infiltrate water, doesn't store water. And then at the end, you have a soil degradation and erosion. So the decline, we need to stop the decline of this soil structure so that we can have an ecosystem function and agricultural productivity. So the loss of soil structure can be due to tillage and crop residual removal. And then the after consequence is water and wind erosion and loss of organic matter and biological activities. So in Australia, a lot of the soil is like this. If you look out, then it forms a crusting, and then after it's crusting, it's a hard setting. That means that it's very hard for the plant to germinate, because it will have problem to germinate. And in some cases, there's also problems with dispersion, because there's lots of salt in the system that makes all the salt, the clay particles disperse. So the stability of the aggregates is very important, because this defines how the carbon hold on or make the soil strong. So this is just a simple experiment. You can do it in yourself. So if you have a Petri dish and you put a soil aggregate, small aggregate and soil, and if you put water in this, you'll see that if the soil starts to disaggregate, this is what we call slaking. And it happens a lot because of the lack of organic matter in the soil. Right, so this is, for example, so before wetting, if you put this in here, so this is the soil. So after wetting, you can see that this starts to disperse. And we can look at this using a digital camera. So what we can capture is over time, if we see how big this aggregate becomes when it's slaking, how big it's become, it will tell us a degree about the slaking of the aggregate. So soil under pasture, soil under grassland will slake, will become, will slake, this is called slaking, but it will not slake a lot. But the soil under cultivated system, for example, here and the crust here, it will slake very high, with a very high slaking. So using this kind of a tool, it can also tell us about the functions about your soil, how soil is functioning. And then it's an indicator of how stable your soil is. And this is all to do with the soil organic matter. So there's an app, it's a smartphone application. So we make this into an app. So initially this is done with a digital camera, but now you can do it on the phone. And this is an app that you can download. So it's based on image recognition. That means that you put the aggregate in, and then it do a segmentation of the image, and then it label it, and then it calculate the area of each aggregate as a function of time when the water starts slaking. So how does it work? Does it work in the fields? This is an example. This is Vertisols in Texas. So they are comparing conventional tillage. That means that the soil has been tilled all over a lot of time, and then the system with minimum, no tillage system, minimum tillage. That means that it's not being tilled, but the residue of the crop is left over in the field. And then this is perennial field, that the field that is not being tilled but being left with the crops that will grow annually. So this is the same. So they do experiment. So the blue one is perennial, and the green one is no tillage, and the red one is conventional tillage. This is time, and this is slaking. So it's done using this app. So they look at how the soil becomes slaking. And what they can see, they can differentiate immediately that the perennial, this one, the one that is always covered, will slake the least, will not slake a lot. But the one with the conventional tillage, it will have a lot of slaking. And this is the coefficient that defines the maximum slaking. And you can see that this is the one with the conventional tillage has a lot of slaking compared with the no tillage and the perennial. And all this degree of slaking is related to organic carbon. Right? That means that the higher the carbon content here, that means that the least slaking it becomes. The higher the carbon content, it will make the aggregates hold on together, stay together, and it's least resistant to slaking. So this is also another data from Australia across New South Wales. They did a survey, big survey. So, and they compare the natural system, the soil under natural vegetation system and the soil under cropping. So this is again the slaking index, how big the soil, after it is immersed in water, how the soil become bigger because of slaking. So you can see under cropping, it will be have a higher slaking compared with the natural system, and it's all related to the carbon content of the soil. That means that if you have higher carbon content, that means it have higher integrity of the aggregate. That means that is less, it is going to be least slaking. That means when rainfall happening, then you would mostly you have aggregated soil, right? So why it is important? It is important because a lot of the agriculture system has what we call a soil carbon loss, because a lot of the agriculture system, especially in Australia, we have a soil carbon loss. So historically, because when people start cultivating, they cultivate every year. They want to make sure that they have a good, can produce lots of crops. So they cultivate every year, and then this is actually from Professor Luo's work in 2010. So this one is in Australia. He looked at different cropping practices at different places in Australia. So this is 0 year or before it is cultivated. And this is how many years, 20, 40, 60, 80 years after its cultivation. And this one is the change in carbon relative to the native lands, the native pasture. That means that the longer you practice, the longer, I think after around 20 years, then you already lose about half of the carbon from your original soil. That means, for example, if your soil originally has a carbon content of 1%, after 20 years, the carbon content will become 0.5, right? So what's the consequences of that, having a low carbon? As you see before, that all this slaking, that means that all this conventional tillage will have a low carbon content. It will have lots of slaking. And with a lot of slaking, that means that the soil is not stable. It's very prone to erosion. That's all in the physical stuff, but also chemically also that means that there's less nutrient in the soil, right? And it will affect the yield, the crop yield. So this is a recent analysis. They look at a meta-analysis, the relationship between organic matter and crop yield. So this is 0% content in the soil organic carbon 1, 2, and 3%. So what you see that there's a relationship, but of course the relationship, it depends on the amount of fertilizer they input, because this is a meta-analysis. They look at different treatments, right? But there's a relationship that the higher the carbon content, the more yield you will get. And I think this plot is probably better. So this is the same data they reported another way. So if your soil carbon is 0.5%, that you'll reach a very low yield, that your yield will be smaller compared if your soil is having a 1 or 2% of carbon. That means that if you want to reach, if your soil is 0.5%, that means that if you want to reach, no matter how much nitrogen you put in, that means that it's not going to increase your yield significantly, right? So from after 100 kilograms per hectare, there's not going to be a lot of increase you're going to expect of the yield. But if you want to increase your yield, that means that it's better for you to increase the carbon content. If you don't increase the carbon content, you are not going to get a responsive application of nitrogen, right? So the soil carbon itself is important, not also physically to protect the soil from erosion, but chemically and for soil fertility. That means that your crop yield will also decreases. And this is happened a lot in Australia, especially in the crop growing area in Australia. For example, this is different places. They all show a similar trend. So after 10 years, after 20 years, most of it declined. So this is originally 1.5 to 2. It becomes around 1. Here as well, 1.5 originally, and then this is 1.6 or 0.7, right? So this decrease is concerning, but then this is also a sequestration potential. That means that there's a potential for us to fill this gap, because this, after 20, 30 years of decrease, that means that there's also potential for us to put this back again, increase again. Because some people say that the soil carbon increase is very small, so it's not worth it. But if you already have depleted your stock, you should put it back. So it's not just for climate change, but it's also for the soil health, to improve your soil. So how do we put it back? So it needs a management that there's a risk and opportunity to capture it by plants. The plant needs to capture it, and then you need to add it in the soil. That means that you don't have a loss of the carbon, right? So what are the data that people say? So this is different places that people look at. So this is in Australia. This is the best management practice. That means that if you change your management practice from the current one to the better one, that means that, and on average, you can increase the soil carbon into 0.3 tons per carbon per hectare per year. So if you convert it into grazing, that means that you convert it to pasture, you probably can get around 0.3 as well. If you put a cover crop, if your soil is put more cover crop, you also increase a 0.3 a year, right? So there are various practices. So various practices. The mean can be around 0.7 to 1.5, depending on what the practice is. So there are it's not just theoretical, but there are some evidence, right? So this is what we call by management to maintain the current system so that the carbon is not going down again, and look for inefficiencies, but also alternative systems, right? Alternative systems so that you can increase the soil carbon. So there's conventional technologies. That means people have practiced it a lot. Crop rotation, that means that you don't just put one crop, different crops. No-till, so when you don't till all the time, or it's probably minimal till. Cover crops, improve pasture system, agroforestry in some area, rice management in rice, because there's also methane increase. That means that over the growing period of the rice, you don't have to flood it all the time, and also peatlands, which we want. There's also in a small farmer system, small scale system, that a combination of the plant and also animal will also be a closed system. That means that if you have a plant, it will absorb the CO2 into plant, but also this plant material can be fed as the food for the animal, and this animal excretion can contribute back to the plant as a fertilizer, and so on. So in a small farming system, combination of the plant and animals, so this will make a contribution, because it's a cropping, it's a closed system. That means that everything, all the waste is being useful. So all the waste of the plant, so the residue of the plant can be eaten by the animals, and all the excretion of the animal can also go back into the system, right? So people have looked at different rate of what are the options, right? So if it's, for example, this is the average greenhouse reduction. That means that the higher this is, they look at this a hectare per year. So these are the potential. That means that these are practices that are going to increase a lot of removal. But this is area of adoption where in the world, where can you put in, right? So for example, rice management, if a good rice management, that means that you can have a high greenhouse gas reduction by managing the CO2, methane and CO2. And if you have a good water management, that is you also have a good CO2. But for large area, so because this is limited to different rice area, this is limited to organic soil. For large area, there's grazing land, there's crop land, there's a lot of opportunities. So, but there's also different technologies that you can look at. So this, what we say before, traditional technologies is, can we put enhanced roots, make the soil grow bigger roots, so, and perennial grains. That means that the grains that are put in not for one season, but it can be for many seasons, and it can have lots of roots. That means that if you have lots of roots, there's lots going to store lots of carbon. Bioamendment and maybe radical soil management and soil microbiomes that still people haven't looked at, that can we manipulate the microbial in the soil so that it can store more, take up more carbon. So for example, in Australia, we talk about radical soil management. Why is it radical? Because it's going to change a lot, because in Australia, there's a lot of system where the topsoil is sandy soil and the subsoil is clay soil. So the sandy soil cannot store a lot of carbon, and there's also problem with hydrophobicity, and the clay soil on the bottom is a problem as well, because water cannot go through it. So what they do is that we can invert it. That means that we have during the tractor, they cultivate it, they make the clay in the sub-horizon, the subsoil, put it on the topsoil, right? So this is, for example, this is the initial soil carbon, right? The black one. So when you invert it, that means that you bring the soil that the carbon, the soil or subsoil that has less carbon to the topsoil, that means that the topsoil now has less carbon. So when you have a system that has less carbon, that means that when you put in more carbon, that means that it will more likely to be, the carbon will be more likely to increase, right? So this is, of course, it's not going to work everywhere, but this is, some people are looking at if you do it at over 100 hectares, a few hundred hectares, it's going to make a lot of changes. And because this is a sandy soil on topsoil, it's not productive, but if you put the clay from the subsoil to the topsoil, that is going to be productive. That means that it's also medium-term increased carbon storage because there's a deficit. If you bring the clay the top that is initially low, that means there's a chance that to increase the carbon content. And we won't go through it. And this is just a survey of practice and different places. That means that first of all, it depends how long it is. This is the sequestration rate per 1,000 per year. That means that, remember we said that 4 per 1,000, that we can increase the rate of at 4 per 1,000 per year. That this is not a permanent solution. That means that it's a limited permanent, and the highest it is around the first 10 to 20 years you can do this, right? And then you can, there's a opportunity within the first 10 or 20 years to increase the soil carbon. And it also depends on the initial carbon stock, right? So if you have a soil that is initially low, that means that you have lots of opportunity. But if your soil is already high in terms of carbon, that means that there's low opportunity. So the opportunity is the area where the soil has been depleted. The soil has been depleted, and that we have to do it within the next 10 years to 20 years. So it's not going to be a forever solution. It's going to be a midterm solution. So we talk about that this is the potential. So what drives this? So what makes this store carbon? So it depends. If we look at it on a continental scale, so for example in Australia, so what are the drivers when we look at the continental scale, right? So in the continental scale, it is a lot to do with the climate. That means the annual temperature and precipitation. That means area which receive lots of rain likely will have more carbon. Why? Because it's going to have lots of vegetation. It's going to have lots of biological product, and areas with higher temperature, you'll have a more decomposition, right? So it's an interaction between temperature and precipitation. And the next is to do with land use. So of course, if it's a forest, then you have a higher carbon content compared with a grassland, and also to do with the cropping land. So, and this is differentiated by the different climates. So if it's a cold and wet, that means you have a lot of carbon content, carbon storage. If compared with cold and dry, or warm and dry would be the least. That means that the potential it's to store carbon is not going to be the same. It's not just the limited by the texture, right? So in the texture, if we look at it, this is, people are talking about saturation curve, right? That means that the carbon content is not going to be increasing forever because there's a limit, right? So that's the saturation curve, but there's also achievable curve. That means that this is what is achievable in the cropping condition, because we know that it's not going to be forever, but we don't want it to be under the critical curve. That means that we don't want it to be going lower on that. So based on that, we can calculate not just based on the texture, but also based on the climate and the vegetation. So if you're under warm and dry condition, you're not going to have under cropland, you're not going to have a carbon content that is, so if you look at it, this is around less than 1%. But if it's cold and climate, the median is around 2%, then it can go up to 5%. But under warm and dry cropland, it's very unlikely that you will going to reach 5% carbon or more than that. So it's more likely you'll go, the maximum will be around 2%. So this is what we meant by you have to recognize that this is the current and this is the achievable curve. That means that if you look at the soil texture, if you look at the climate, and you look at the land use, then means that you have can look at how much potentially you can increase. And then this is, for example, our calculation. The cropland, the topsoil currently is the storage is this, and this is the potential. That means that it's under 4 per 1,000 if you increase the carbon content 4 per 1,000 every year. That means that within 60 years you can achieve a potential higher carbon content. So I think we won't worry about this because this is Australia. So this one, finally, we talk about how can we look at it at a global scale. So, and again, at a global scale, you see the effect of climate. So this is area with a cold and wet, you have a higher carbon content. And the tropical area, although it's hot, but it's have a high rainfall, you will likely to have a high carbon content. But we look at also how the soil carbon change with time. And then to do that, we did of modeling by looking at how the soil, the land use has changed. And then by looking at from 2001 and 2016, we calculate where the area has changed from the native vegetation into cropland. For example, here, we look at the satellite images. So this is 2001, a lot of it is still under forest. And in 2013, you can see part of this is already being deforested. That means that this is the likely soil organic matter changes will be in this area where there's lots of changes in the land use. Right, so this is the carbon stock. That means that we calculate the carbon stock topsoil, and then the losses that's overall in the whole world, that per year, every year that you lost about 2 per mil or 0.02% from the initial stage. But a lot of it happens in and around the tropics and subtropics. But the effect of this is that a lot of the area is under the critical limit of 1.1% in the tropics. That means that in tropics, if it's less than 1%, that means that your crop productivity will be affected. That is a lot of area. It has a very low carbon content, right? But that means that, for example, in the tropics, there's about 11 million hectare per year that is going to be decreasing, and in temperate there's about 4.36 million hectare per year. That means that there are a lot of opportunities to restore the carbon to increase the productivity. So can it be done at a large scale? So what are the evidence, right? So people say that maybe that's theoretical, it's not possible. So at least in some areas, we can show that, so for example, this is the data in South Korea, the topsoil. So they have a monitoring program starting from 98. So in the plastic house, orchard, paddy, and upland. So all of it, there's an indication that there's a positive budget over time, a positive carbon increase can be achieved. This is an analysis in China by Zhao. He's from the Soil Science Institute in Nanjing. So they compare different area in 1980 and 2011. So in a lot of places, there's a positive change, right? The change in positive, except some places in the north, a lot of area, there's a positive change, and the positive change is because of increase in the management, because there's a lot of carbon input from the root, from the straw. So overall, there's an indication that over large scale, there's the soil carbon can be a positive. So this is just an example. This is from Song Chao, from ex-Zhejiang University, now in France. So they also look at calculating the potential in France. So this is very end. So this is, of course, it's a complex situation. It's not just a scientist. So scientists, is our job is to do the measurement, sensing, and modeling. So to give an idea about how much carbon in the soil with digital soil mapping, and we need to do research about how the soil carbon is functioning, how its persistence in the soil can be kept in the soil. But the one who's working out is the land managers or the farmers. And we need to also inform the people in the policymakers that increasing carbon is an important thing. And by the end, then if you put it in the market, that means that it can be a carbon trading. That means that the farmer who is doing a management practice, that they can get payment for that. So that's about it. Thank you very much. And if there's any question, you can ask. I think if you type on the chat, I can try to answer it. If you're shy to speak, you can type on the chat board.
Thank you, Buddy. It's a very impressive presentation. It's also very informative, from the local scale soil structure to the global scale soil carbon sequestration potential. Thank you very much. Any questions? Okay, I have a question. At the start of your presentation, you said that you give us some results of the relationship between soil carbon and soil structure. But based on the, for example, if we consider the drivers of soil formation, how can we consider the effects of soil mineralogy or the topograph on the soil formation, like this thing, and how does this correlate to soil organic carbon? This is the first question. And my second question is, there are some results about the relationship between soil organic carbon content and the yield. Can you give us more information? What's the underlying mechanisms driving the positive relationship between soil carbon and the yield? Perhaps my guess is that soil water is also very important, because soil organic carbon would increase the soil water holding capacity of the soil. Anyway, I would like to hear your opinion. How can we consider, because in cropland, in agricultural soil, if we want to sequester carbon, actually we also sequester nitrogen or sequester other nutrients. How can we consider the trade-offs between carbon sequestration and crop yield? Yeah, that's my question. Thank you.
Thank you, Professor Luo. Yes, I agree about the minerals. So it's also depending on the mineral. So I mean, the ingredient, of course, to make the soil structure is not just organic matter, because you also need the clay and the types of clay, and also if your soil is only sand, that means that it's impossible or it's unlikely that you will form a good structure. So it's all the interaction between the clay minerals, and also the organic matter. But I think organic matter itself also has an importance. So because if you have just mineral content, if you just have mineral content and you lack this organic matter, that means that the aggregate it forms, it's not strong. It's going to fall apart. That's why what people see in this slaking is that the moment that this thing is that the moment that you put water in, although the soil can have a high clay content. So this is all vertisol. This is all vertisols in Texas. the Vertisol is famous because it's have very high clay content. The moment that you lose this carbon, that means that the slaking, that means that the ability to hold more bigger aggregates or macro aggregates is lost. You don't have that capacity. Under the small micro aggregates, all the clay particles can still form, but under a bigger aggregates, it doesn't have the ability to hold together. So that's why in a lot of field, especially in Australia, so what you see that you have the surface that looks like this, right? Because if you don't have this kind of aggregation and the soil cover is bare, that means that at the end, if you have rain, that all this is going to clog up the pores. That means that it's going to cause erosion. Okay, so that's the second one is about the relationship with yield. So it is very hard to find I can find it. It is very hard to find this paper is a meta-analysis, and the relationship is not clear, and it's understandable because it is affected a lot by, as you say, about the water and also about the other nutrient. But generally you can say that in addition, so if you look at this is nitrogen input. So if you have a low carbon to start with, and know that if you put a bit of fertilizer, you can expect an increase in the yield. But after that, the general increase is not that high. It's not that significant, right? The same with this, and if you increase the nitrogen input, if the carbon content is low, that means that you're not going to expect to have a lot of increase in the yield because the nutrient supply and I think the ability for this to hold the nutrient, and also in addition to nutrient, as you say, about the water as well, it doesn't have that much because of the structure is not that good. That means that all the water in the rain is not going to infiltrate very quickly. That means there's not a lot of opportunity to increase the yield. But once you increase the carbon content, that means that there's also potential that if with nutrient, that it also work together, right? So, I mean, yeah, it's looking at data is very. I agree with you. It's very difficult to untangle all this relationship because there are lots of different factors, but I think it's an interaction between nutrient supply and water is important. And then there's also another thing about people talking about increasing carbon needs nutrient, needs nitrogen fertilizer. I think this is true in some cases, but not all the time, because what you're supplying is what the carbon comes from is carbon come from the yield. Right. So in order to have the yield, you already fertilize the soil. You already have fertilizer, and in a lot of the cases, probably nutrient is not the limiting factor because nutrient use efficiency in cropping is very poor. Most of the time, farmers over fertilize the field. Right.
Okay, thank you. Any other question?
Hello.
Yes.
I have a question. Good afternoon, everyone. I'm from Chinese University. I have a question. The background is with the Tango, people more focus on the soil health. Before, maybe focus on the soil quality. With the focus of soil health to food health to people health. My question is, focus on the soil health. Maybe we'll choose chemical, physical, or biology indicators. What will we choose the indicators to elevation the soil health? That is my question.
Thank you. Yeah, it's a good question. So a lot of people nowadays talk about soil health, and it's not a clear definition. It's very popular and people like it because it related to human health. But what is a healthy soil? That is still debatable, right? So if you ask a question, what is a healthy soil to 10 different people, you probably get 10 different answers because there's no clear definition. And what defines a healthy soil, right? So that's it's not clear. For example, can I say that my soil carbon is 1%, so I have a healthy soil? It's not necessarily true, right? So if my pH is low but my carbon content is high, that means that I have an imbalanced system. So it's soil health is very subjective and there's no clear definition. So some people say that it's to do with a lot of microbes in the soil, but how do you measure microbes? What is a good number of microbes? And people cannot tell you that. Yeah, so at the moment I think it's an unclear definition from a scientific point of view. It's an unclear definition, and we probably should avoid it in terms of the scientific terms.
Thank you.
Yeah, I would think that we can combine pH and soil organic carbon as an indicator of soil health. I'm not very sure. It's an open question. Everyone can get some idea about how can we infer soil healthy. It's also very important, I think. Yes, thank you. Any other questions from the room? No? How about from the online, the people online? Any other questions? Okay, thank you. Thank you, Bulman. It was 1 hour and 10 of this time. Yeah, 1 hour, 10 minutes already. So thank you very much for this course class. I learned a lot actually. I believe our students also learn a lot from this presentation. Okay, thank you.
Thank you. See you next time.
See you next time. Bye-bye.
Bye. I can leave now.
还有什么要说？